Hi, in this video we are going to talk about another operation as far as binary search trees are concerned, the so-called deletion. So let's consider the easiest way of removing an item or a node from a binary search tree, and this is the soft delete. We do not remove the node from the binary search tree, we just mark that it has been removed, and then we are not going to bother about it when further bump into this node. Of course, it is not that efficient solution. So, in the main, there are three possible cases. The node we want to get rid of is a leaf node, or the node we want to get rid of has a single child, or the node we want to get rid of has two children. So let's consider the first one. When we want to get rid of a leaf node, basically, it's very simple, we just have to remove it. For example, set it to null, whatever. So, first we have to search for the item we would like to delete. We start at the root node, 5 is smaller, we go to the left, 5 is greater than 4, so we go to the right, and this is the item we would like to get rid of. We just set it to null. So we set the 5 parent, which is the 4 right child, to be equal to a null. Okay. So the complexity is we have to find the item itself, plus we have to delete it or set it to null. And the overall complexity will be logarithmic, because first we have to find the item, it takes logarithmic time complexity, and then we have to remove it. It is ordo 1, so constant time complexity, but the overall complexity will be logarithmic, ordo log n. Okay, what about the second case? We want to get rid of a node that has a single child. We just have to update the references. So we would like to get rid of the node 1. First we have to look for it. So we go to the left until we bump into the node 1 we would like to get rid of. So basically we just have to set the parent's pointer to point to the child instead of this one. So we just have to get rid of this and make sure that the 4 is pointing to the -2 instead of the 1. We can do it very easily, we just have to update the references. Okay, so the complexity is first we have to find the item, and then we have to update the references and set the parent's pointer to point to its grandchild directly. So the find operation is logarithmic, the updating the references is constant time complexity, so the overall complexity is log n, logarithmic. Okay, then this is the most complex case when we want to get rid of a node that has two children. We have this binary search tree and we would like to remove 32. We come to the conclusion that this is the root node, so we have two possibilities. First, we look for the largest item in the left subtree, or we find the smallest item in the right subtree. So, in the left subtree we have to find the greatest item. This is called the predecessor. This 23 is the predecessor of 32. Or we have to find the smallest item in the right subtree. This is the 55. It is called the successor. So the 55 is the successor of the 32. Okay. And then we have to swap the root node, for example with the predecessor. We could swap it with the successor as well, but in my implementation I'm going to use the predecessor. So we have to swap them. And okay, why is it good? Because we will end up at case 1 or case 2 when this 32 node in this case doesn't have any children, so it is a leaf node. We know how to get rid of it, we just have to set it to null. Or we are going to end up with a situation that we know for certain, for example when it has a single child. So we know for certain when we swap it with the successor or the predecessor, we are going to end up a situation that's the case 1 or the case 2. So we know how to deal with these kinds of situations. I think it is a very elegant algorithm. So we just have to get rid of it. But let's consider the fact that we swap the root node with the successor just to make sure that it is working fine as well. We swap it with the successor, and as you can see now, we have to get rid of a node that has a single right child. We know how to deal with it. We just have to set the root node to point to 79 directly instead of 32, and we have to set 32 to be null, so we have to remove it. Okay, and basically just have to update the references. So what about the overall time complexity? First, we have to search for the items, then we have to swap it with the successors, so maybe we have to search for the successors. All these operations has logarithmic time complexity, so we have to add up logarithmic time complexities. Of course, we have to update the references in constant time complexity, so we're going to end up with a logarithmic time complexity algorithm again. So all of these operations have logarithmic time complexity. Why is it good? It is a very predictable data structure as far as running time is concerned. So that's all about how to remove items from a binary search tree, and we have considered 3 cases. The first 2 is quite intuitive, and the third one is going to be reduced to the first 2 cases. So I think that it's a very elegant way of implementing deletion operation in a binary search tree. Thanks for watching.